Hey everyone, and welcome. Today we're going to jump right into the physics of motion, and we're going to see how the exact same rules that explain something as simple as a cyclist hitting the brakes can also help us solve a truly massive puzzle. And here it is, the big one. Just imagine it. You're standing at the tippity top of the tallest building in the world, the Burj Khalifa, and you drop a coin. How long does it actually take to hit the ground? I mean, that sounds crazy complicated, doesn't it? Well, turns out we can figure it out with just a little bit of physics. And the secret isn't some super complex computer model or anything like that. Nope. It's hiding in plain sight, tucked away inside a handful of really elegant and powerful equations. So to tackle our skyscraper-sized problem, we first need to build up our toolkit. So let's get that toolkit assembled. And I want you to think of these next few things not as, boring textbook variables, but as the fundamental language of motion. These are the words we need to describe how basically anything and everything moves around us. Here they are, our 5 key players. First up, we've got S for displacement. And really, that's just a fancy physics way of saying the total distance something has traveled from where it started. Then we have 2 types of speed, U for the initial or starting velocity, and V for the final velocity. Next is A for acceleration, which is just any change in an object's speed, whether it's speeding up or slowing down. And finally, the one we all know and love, T for time. And believe it or not, these 5 little variables are all we're going to need. And this is how we put them all together. These are our equations of motion. Think of them like master keys. Each one shows a different relationship between those 5 variables we just talked about. With just these 3 formulas, we can unlock pretty much any problem that involves a constant acceleration. It's awesome. Okay, so let's dive in. Before we go and climb the Burj Khalifa, we really need to get comfortable using our new tools, right? So we're going to start with a couple of smaller, everyday examples just to see how these equations actually work. Welcome to the training ground. All right, let's kick things off with a simple one. Picture this. A car is just sitting at a standstill. The light turns green, and it starts accelerating at a nice, steady rate for exactly 10 seconds. So the question is, how far did it actually go in that time? The first step in any of these physics problems is to play detective and find the clues. You see that phrase from rest? That's a huge clue. It's telling us the initial velocity, u, is 0. The problem also gives us the acceleration, a, and the time, t. So the only piece of the puzzle we're missing is the displacement, s. Now we go back to our toolkit. Which one of our equations has the 4 variables we're dealing with, s, u, a, and t? Well, it's this one right here. It's the perfect tool for the job because it connects everything we already know to the one thing we want to find. So we just plug in our values, 0 for u, 2 for a, and 10 for t. Now that first part of the equation, ut, just becomes 0, which makes our lives way easier. And when you crunch the rest of the numbers, boom, you get a clean answer. The car traveled exactly 100 meters. See? It's not a guess. It's a predictable result. All thanks to picking the right equation. Let's try another one, just to make sure we've got this down. This time, we've got a cyclist who's already cruising along, but then they slam on the brakes, coming to a complete stop in 5 seconds. This time, we want to find their acceleration, or you could say their deceleration. Okay, same process. Let's break it down. We know their starting speed, u, and that phrase, comes to a stop, is another one of those big clues. It tells us the final speed, v, is 0. And we know the time, t. So our only mystery variable here is the acceleration, a. Back to the toolkit we go. Which equation connects v, u, a, and t? That's right, it's our first one. This is a perfect example of how you just look at what you have, figure out what you need, and then select the formula that fits. So we plug in our numbers, do a little rearranging of the formula, and we get our answer. But wait, notice that negative sign. Don't let that throw you. It's actually telling us something important. In physics, a negative acceleration just means the object is slowing down. That's it, it's decelerating. All right, I think we've pretty much mastered the training ground. Now, take a look at this. An accelerating car and a falling coin. They seem like they're from completely different worlds, right? But to a physicist, they're practically the same thing. Seriously. They both start from rest, they both cover a distance over a period of time, and here's the most important part, they both have a constant acceleration. For the car, it's the engine making it go. For the coin, it's gravity. The physics is exactly the same. The scale is just way, way bigger. And now that we've got our tools and we're feeling confident, it's time. It's time to go back to that massive puzzle we started with. Let's solve the Burj Khalifa problem. And guess what? We're going to follow the exact same process. Step 1, let's identify what we know. The distance, s, is the height of the building, 828 meters. The coin is dropped, so its initial velocity, u, is 0. And the acceleration, a, is the constant pull of Earth's gravity, which is about 9.8 meters per second squared. Step 2, choose the equation. Just like with our car problem, the perfect tool for this job is s equals ut plus half at squared. Which brings us to step 3. We'll just need to do a little algebra to rearrange the formula and solve for our unknown, t. We plug in the numbers, we rearrange that formula to solve for time, and we get our answer. Just about 13 seconds. Just think about that for a second. An object falling almost a full kilometer, and it only takes 13 seconds to get to the bottom. That is the incredible, relentless power of gravity, all revealed with one simple equation. So, why does this all matter? I mean, it's definitely fun to solve a puzzle about the world's tallest building, but what's the bigger picture here? What's the real takeaway? Well, what we've just done is a whole lot more than just math. We used a simple language of variables and equations to make a precise prediction about the physical world. These formulas, they let us look at a situation, understand the forces at play, and know with a ton of certainty what's going to happen next. It's how engineers design roller coasters that are both thrilling and safe. It's how astronomers predict the paths of planets millions of miles away. And yeah, it's how you know how long you have to brake to avoid running a red light. But of course, our calculation was done in a perfect little physics bubble. The real world, it's always a little bit messier. So I'll leave you with one final question to think about. We ignored one really crucial real-world factor, air resistance. How do you think that force would change our answer? Would the coin in the real world fall faster, or would it be slower? Thanks so much for joining me.